there are really three, and arguably only three, sustainable cycles. There's a water cycle to hydrogen and oxygen. We can close that loop through making electricity right now, and, as I'll show you, without making electricity, but directly from the sun. There's two other loops. There's a carbon dioxide loop from the air, where we're going to reduce it and make some reduced thing, and I'm agnostic about what we make. CHOYHZ, some gasoline or hydrocarbon or diesel, whatever it is, and then we're going to oxidize that. We'll run that backwards. And there's a nitrogen cycle. There are two, but we're going to stay in the reduced nitrogen cycle. Nitrogen to ammonia and back again. And we would do, and the point here is these are the only three sustainable cycles, really biogeochemical. They're all abundant. They all have advantages and disadvantages. The disadvantage of running a carbon cycle for your liquid fuel is the carbon ultimately has to come from the air when it's 400 ppm. It's harder to source that than it is to source water from the air or nitrogen from the air. And so it's an easier transformation to source from more abundant things. It's harder to do this, but you may have applications in where you're forced to do this because you simply don't have the quality of energy services for some of these gaps that you can get this way. Or you may not want to transition that way. If we drive a water cycle to hydrogen, we already know chemically how to drive these other cycles. So with established technology, with the Haber-Bosch process, we can fix ammonia from nitrogen and hydrogen done at global scale. It makes fertilizer. 10% of the energy is consumed this way to make methane, to make hydrogen, to make ammonia already on our planet. This is done. You won't need cheap nitrogen capture to do this because we can get that, right? It just comes from the air. It's pretty easy. We can also drive, in a two-step process, electrons to hydrogen and then drive this. This is known by several pathways. One is CO2 and hydrogen to make so-called syn-fuel, CO and hydrogen, and syngas to make synfuel. There are other preferred chemical pathways now. You'd make methanol and methanol in the gasoline. We know how to do that too. So we could give you methanol, carbon neutral. We could give you gasoline, carbon neutral. The key ingredients you need to do that are you need cheap, renewable, clean hydrogen and direct air capture of CO2. The rest of that is done, okay? So now the question is, in filling these gaps, which I haven't yet heard anything that would say that there are certain things that we don't need a liquid fuel for to help fill those gaps, both grid scale storage and these transportation that Lee agreed we have to solve, that we're compelled necessarily to solve them all with liquid hydrocarbon fuels. If you put on the table that you can, say, in the heavy-duty trucks, store your energy as ammonia and then crack it to make hydrogen to run your fuel cell, or just directly burn it in an internal combustion engine, which both can be done, you don't need to have direct, cheap carbon capture to enable this cycle to occur. Because all you need to do is directly split water to hydrogen, and then you're off to the races. So this is enabling for this cycle and for this cycle, but it needs cheap direct capture, which could occur by one of two methods. It could occur by people doing it, with Klaus or somebody inventing it, or it could occur with nature doing it, with bio capture. It's not clear to me at all that we have to depend on plants to do the stuff they don't do very well, which is store the energy. But we do have to depend on them, maybe as an option to capture the CO2 and to fix it into some form that we can inject the energy. Because if you take hydrogen and take a not very energy-rich biofuel, you can actually store almost all the energy in those HH bonds in the CH bonds you make when you reduce that fuel. And so you can run the carbon cycle without having to worry about the efficiency of photosynthesis by getting your efficiency this way, stored energy, and then converting it to the liquid fuel, provided you've got a cheap CO2 capture. The energy storage in the liquid product can be completed that way. Okay, so this is kind of Fuels 101 in the same way that you think about all these electricity things for the people that may not be thinking about that very much. If we want to drive this from renewable energy source, from wind, the only way we can do that now is make wind to electricity, put it into an electrolyzer, make hydrogen, and then drive one of these cycles. We can do that, but as we heard, but you need to hear a little more, the capital expense associated with the electrolysis unit, that transformational gizmo that's going backwards on the energy scale because we're taking high value energy electricity and converting it to low value energy fuel, we do the other way normally, that we pay capital to do that backwards transformation. That capital's very expensive. And so right now electrolysis, which is practiced at scale, 100 megawatts was practiced at Aswan Dam in the 1980s in alkaline electrolysis. Not 1 megawatt is a demonstration, 100 megawatts. And chloralkali, a closely related technology, is 4% of the electricity on our planet. And that's used to make chlorine. And it's very similar in its balance of systems and implementation as splitting water into hydrogen and oxygen, except that you sell the chlorine, in which case here we'd vent the oxygen. We know the costs of that. It's way too expensive in capital, even if you had cheap electricity, in order to make hydrogen at a cost-competitive price with what we would have on a joule equivalent of gasoline from fossil energy today. So what you need to do in order to make this process is, in addition to having ultra-cheap electricity, you've got to have a disruptive way to do electrolysis. Okay? I think it can't be any of those laundry list of things that we heard from Jack Brower as practiced the way they're practiced at scale, because they just cost too much money, and we know that. We can't learn them out to the lowest cost. The fundamental reason for that is electrochemistry, just like batteries, are two-dimensional systems. You need electrodes, you need planes, and the chemical transformations to scale into large volumes are three-dimensional things. You build the skin and you fill the volume with your reactants. But in a battery and a fuel cell and electrolysis, you have to build all the plates to fill the volume, so you pay a lot of capital to get a lot of current through the system. And that's a fundamental problem that we somehow have to overcome. Okay? But I think this is really important, because if we had a cheap transformation from the electrons into protons, then you bridge stationary and mobility, you have a grid scale storage, you do everything with chemical bonds in a clean energy economy that we now do in a fossil energy economy. And I'm agnostic about in which form you do it, provided that you have cheap direct air capture, either biologically or not, because if you don't have that, you close this cycle and you've got to depend on these two. Okay? Now what do I do in my non-hobby, which is energy systems? I have for a while thought that it would be a good idea for humanity to take the biggest energy source, other than a nuclear fission reactor, fusion, the sun, and convert it into chemical bonds, just like nature did. That I think ultimately, 1,000 years from now, a couple hundred years from now, that's going to be, it's inevitable. We're going to take the biggest energy source, the sun, and we're going to store it in the most dense form other than the nucleus, which is chemical bonds. It doesn't make sense, if you could do it, to do that through electricity, because you went to high value energy electricity and then back again, and nature doesn't do that. Nature directly makes chemical bonds from the photon energy of the sun. Nature only does that with 1% efficiency at best. So A for inspiration, D minus for execution, okay? All right? Any engineering design class, you say, build me a gizmo, it's 1% efficient, you don't pass that class. Okay? Plants pass the class because there's a lot of them, right? But I think that if we depend on that, we are fundamentally depending on a 1% efficient system to give us the lignocellulose energy content, and then it's downhill from there to try to get trade food for fuel and land and everything else, that we have the ability to find a way to do that at a much higher efficiency so as to have much less capital and much less land use. Okay? This won't work and won't contribute unless we do that. So that means you have to have 10% efficiency, and it has to be cheap because you're covering large areas. The advantage of using a direct electrolysis is you can have a higher capital utilization factor, because you could feed electricity from wind and solar into a central station electrolyzer that could run 80% of the time. So we know how to do that, not cheap enough, but it's the competitive technology evolution that I think we should be exploring. How do you make ultra cheap electrolysis to bridge those things that honestly nobody's doing? Okay? Now in that framework, we're going to give, I mentally say, somebody, maybe us, will think about ultra cheap electrolyzers. Can we do even better than that by not having to make electricity as the intermediary and just doing it all chemically, photochemically, and making a fuel? Okay? That's my job. That's what my research program's about. There's a whole collection of people doing what we call solar fuels, which is to do exactly that, to develop catalytic systems that take, in its early implementations, take sunlight and water as the only inputs, and water can be water vapor from the air. It need not look like a solar panel. It doesn't have to be plumbing, because if you look at the solar photon flux and compare it to the kinetic theory of water just from humidity, you have plenty of water vapor with a little sprinkler system maybe like your grass to take what looks like astroturf that you've rolled out and just collect the products through a drainage pipe. Okay? And that's the idea. Okay? So this does not look like solar panels. It does not look like solar thermal plumbing. It looks basically like astroturf with drainage pipes in our dreams. Okay? But that doesn't mean we can't think about doing it. Right? It does mean that it has to look like that. If it looks like a solar panel and you've got a solar PV on top of an electrolysis unit, you're never going to beat the central station 80% capital electrolysis connected to wind and solar. So don't make it look like that, because you can't win. Okay? So that's kind of our design philosophy. How many minutes do I have? Perfect. Look, I'm happy to tell you and dig into our technology like crazy. It's not technology. It's in the lab. It works on a scale this big in a piece of plastic on my thumbnail. It lasts for about a few hundred hours. We have challenges in terms of materials. This is not an engineering project. We've demonstrated we can, with 10% efficiency, direct efficiency, total sunlight in, total fuel energy out, split water into hydrogen and oxygen without making explosive mixtures. You can collect the hydrogen under pressure. You can do all this good stuff. We also know that we can't directly do that with CO2, not because there's a catalyst problem, which there is, but because we have to have concentrated CO2, because 400 ppm doesn't give us enough flux to match the solar flux. And so we have to have a coupled source of direct carbon capture. And if we do that, then we have to ask the question, is it better to do that chemical transformation up front or pump the hydrogen into a chemical plant that can use known chemical processes to do that later on? And that trade, I think, favors the chemical plant later for scale purposes, but we'll see. Okay? So this is our philosophy. This is what we're trying to do. And again, I'm happy to tell you all much more about it if you ask me.